Hi, I'm Daniel George. I'm a PhD student at the University of Illinois, and I work at the National Center for Supercomputing Applications. So my talk will be about deep learning for time series signal processing in the context of gravitational wave analysis, especially LIGO. So I will show how to design and train a neural network in the Wolfram language, and how to use pre-trained net models to classify anomalies in noisy data streams from the LIGO detectors. So I'll be talking about 3 projects that I did using the Wolfram language related to gravitational wave analysis for LIGO. Um, so this is work that was done at NCSA recently. And I'll get started now with the first project. So first of all, to give you a brief overview, gravitational waves are these ripples in the fabric of space and time. They're predicted by Einstein in 1916, and we actually detected this for the first time in 2016, exactly 100 years later. So you can see that when really massive and dense objects like black holes and neutron stars, they spiral in and merge, they release these waves that we can actually even measure billions of light years away using detectors such as LIGO, which use laser interferometry. And this is how the gravitational wave signal looks like when a pair of black holes merge. And these are the 2 detectors that we have right now in the 2 opposite corners of the United States. There's one more in Europe. It's called Virgo. It just started running recently. And there are more coming up soon. So we have actually detected 4 black hole mergers so far. One of them is likely to be a false detection, so we're not sure about the second one, but we have 4 detections that are 3 detections that are confirmed. And last week, the Nobel Prize was awarded to Kip Thorne, Ray Weiss, and Barry Barish for leading the LIGO collaboration. And then on this Monday, we actually announced that we detected a pair of neutron stars merging for the first time. And what's special about this is that we can actually detect light from this event. Unlike when black holes merge, it only emits gravitational waves, whereas neutron stars actually emit light all the way from gamma rays to radio. And we actually observed this with 70 telescopes, and this leads to groundbreaking insights in physics. But the challenge that we're facing right now is that signals are really weak. Most of the signals have a signal-to-noise ratio less than 1, so you can actually see them in the time series or in the spectrograms. So this is actually how it should look like. So these signals are buried in noise. And how do you detect signals that are so weak? So one advantage we have is that we can solve these physical events on supercomputers like Blue Waters, which is like right next door. And we know what gravitational waves should look like. So we can actually try using a template matching method. So it's basically a classification and regression problem. You have some input data, and you want to find what is in it. So you want to classify it as a signal or noise, and you want to measure what the masses of the black holes are, and what the masses of the neutron stars are, et cetera, like supernova. So what they do right now is they have a huge bank of these simulations. So you can imagine it's like cat and dog photos. You're looking for cats and dogs in your data. So you have this huge album of simulations of cats and dogs or gravitational waves, and then you try comparing every input with every data that you get from your detectors, and you see if there's an exact match. And this is not at all scalable. You'll need trillions of simulations to actually do this kind of analysis. So this is what is going on right now. So they're only looking at a small subset of signals. So what we want to do is to scale this to all possible signals. And the solution is, of course, deep learning. So the idea behind deep learning is you stack a bunch of neurons, a bunch of layers together, and these very deep network of neurons actually are very good at learning patterns in the data. So you don't actually need to keep all these templates and compare inputs one by one. Instead, you can train a network, and it generalizes to the full space of signals from a limited amount of data. And this is very successful from all areas, including speech recognition, face recognition, self-driving cars, all kinds of things. So these are some applications that are happening right now. So you can see it's being used in medical diagnosis. And these captions are actually generated by a neural network, and it's really accurate. And for example, when Facebook tags your photos, it's using a neural network. And Google Assistant, Siri, et cetera. Oops. So yeah, the basic idea behind neural networks is you start off with a bunch of neurons, and you set it with random weights. And then you iteratively tune the weight so that the error on your training data is minimized. So it's basically an optimization problem. You have some label data, and you want to fit the weight such that the error surface is at a minima. So you're at the minima in the error surface. And what we are using here is called a convolutional neural network, and it's commonly used for image recognition. You can see that since about 2015, it's more accurate than humans at classifying images. Basically, the ImageNet dataset is a bunch of labeled real-world photos. And each layer actually learns hierarchically different simple features, and they combine it to create the final input. So this is actually much more efficient than doing template matching. So here what we did is we used a convolutional neural network for doing 1D with 1D inputs. So it's commonly it's used for images and video, but here we applied it to 1D time series data. And we use data from LIGO detectors. And there is a lot of advantages of doing this because you have architectures like GPUs and FPGAs, which are very efficient. So you can do the analysis in real time on site instead of doing this on a cluster of hundreds of thousands of GPUs or CPUs that they're using right now. And these neural networks are only a few megabytes, whereas the template bank that is used to train it was like gigabytes of data. And the most important advantage is that you can interpolate to templates between your training data, whereas the current template matching methods can only find the templates in the bank. So the signal should match exactly. So this is a huge advantage. We started with very simple convolutional neural networks. You can see there's 3 convolution layers. This is in the Wolfram language, and a couple of fully connected layers. And we have 2 neural networks. The first one tells you whether there's a signal or not, and the second one, if the first one says yes, then you apply the second network, and it'll tell you the masses of the black holes that produce the signal. So I can actually show you the code to do this in the Wolfram language. So basically, you just get some training data, then you make a function that generates training data like this. So it pairs of data. So you have noise, you have signal, and then you label this as false and this as true. And then you train this net, which is a very simple. So it's just a few lines of code. And this is the network. And here you have the training. So when I actually did this, I did not know anything about machine learning or neural networks at all. All I read was the documentation. So I did this the moment that this functionality came out. And then I got the results, and then while I was writing the paper, I had to actually understand how all this works to write the introduction. But so this I did like back in December. So yeah, so you can see the error going down with iterations. And then you can stop it. Let's see. So now you're testing it on a test set. So you're adding Gaussian noise to a signal, and you're seeing if it works. And it says true, and then if you input just pure Gaussian noise, it says false. So even with just like 5 seconds of training, it's already working. And then you can also do the same thing for estimating the masses. I'm not showing that. It's the same thing. Instead of labeling true and false, you label it with the numbers of the black hole masses. And this is the comparison with the current method, which is called match filtering. So on the same CPU, the neural network is like 100 times faster at doing this detection and parameter estimation. If you actually use a GPU, it's over 5,000 times faster, which is a huge improvement. This means that you can analyze the data as it's coming from the detectors. And even thousands of seconds of data can be processed in less than 1 second on a cheap GPU, like a gaming GPU. So, and I actually compared with all the other methods in the classify function in mathematics, and you can see that the neural network is much, much better for both detecting the signal and also for estimating the masses. So 50% accuracy here means it's just randomly guessing. So for these noisy signals, the traditional machine learning methods don't work at all. And now we actually trained this with real LIGO data. And you can see there's all kinds of glitches in the spectrograms. So it's not just pure Gaussian noise. But we found that it still works for real data, even though we only trained it on Gaussian noise. So this is a comparison on what percentage of signals are detected versus the optimal signal-to-noise ratio. You can see that it's almost the same as the current method that they use for the signals that we train, because we use the same template bank. But for estimating the masses, the neural networks are much more accurate because they can interpolate to regions within the template bank. And one additional advantage is that the deep learning method is resilient to all kinds of anomalies that show up in the data, which are not signals, it's just glitches in the detectors. So the network can automatically recognize the difference between these and the signals. And finally, if you actually have a period of bad quality data and a signal happens to occur during this data, the neural network can still detect it with over 80% sensitivity or accuracy, which is not, these signals would be currently missed by the techniques that LIGO uses now, because whenever there's a region of bad quality, that data is removed. So this means that we can detect signals that could have not been found yet, but we haven't yet applied this to all the LIGO data so far. And here I have a demo. So I'm showing, it's not playing, it's supposed to play. See. So this shows the first gravitational wave event. And you can actually slide the neural network through the event, and when it reaches the signal, it tells you the masses, and it tells that the gravitational wave was detected. So this is so fast that you can actually even run it on your GPU on a laptop, or even on your laptop CPU. Whereas for actually detecting this, they use hundreds of thousands of CPU hours for doing the full parameter estimation. All right then, and another advantage is that we only trained with black holes on circular orbits, but the network is still able to detect these weird signals that happen to occur from black holes on elliptic orbits. And the current methods always miss these because they don't use these templates. So this means that the networks can generalize to new kinds of events that would be missed by current methods. Okay, and this is the second project that we did recently. Here we want to actually find anomalies in the data set where we don't have any models. So you don't know what you're looking for. So how do you find events like these? So here what we do is we use transfer learning. So you have these data sets of all kinds of weird anomalies in the LIGO data, and it's been labeled by humans. So we have a small data set of around 6,000 images like these, hand-labeled by humans. And we want to now train a network. Usually you need like hundreds of thousands of input data to train a neural network, but if you use this approach called transfer learning, where you train a network on real-world objects of like cats and dogs and planes and things like that, and then you can fine-tune that network on your data set. So it can learn from a small amount of data. This is exactly why humans are good at learning really fast, because they already have a model of the real world internally. So for this, we use a network trained on ImageNet, which is a huge data set of millions of images. It's actually being used by Image Identify. Actually, a larger data set is used by Image Identify. So we used a model called Inception, and after just 5 minutes of training, we got state-of-the-art results. We got over about 99% accuracy, whereas the previous work done by another group was around 96%, and they had to train for hours. So I can actually show you the code to do this. It's actually just a few lines in the Wolfram language. So what you want is to first get your data set. So this is what it looks like. It's just a bunch of images labeled with 22 classes. These are the 22 classes. And then you get a net model. You get a pre-trained net from the neural net repository. So this is one of the state-of-the-art nets. It's called Inception v3. So it's originally designed for 1,000 classes of like real-world objects. Oops. That's weird. OK, anyway. So now we need to change the number of classes to 22, because that's the number of classes in our data set. So you actually take up to the 4th last layer, and then you attach 22 neurons to the last layer, and then you add a softmax layer. So it's kind of simple. So now you have a new net with pre-trained weights designed to classify 22 classes of objects. And then you fine-tune it by training this modified net on your data set for just like 5 minutes. You usually need a GPU to do this because this net is a giant neural net. And once that's done, I'm just going to stop the training here because I don't have a GPU. Oops. OK. And then once you have this net it is very accurate. We got 99% accuracy at finding these signals. So these are spectrograms of LIGO data, and we can classify them into these 22 classes with 99% accuracy. And all right, so this is a classifier. Now we can also use these classifiers to find unknown, unlabeled classes of objects. So this is called clustering. And here what we do is once you train this neural network, you can cut off its last layer and use it as a feature extractor. So it converts an image into a bunch of numbers that capture some meaning about the input image. So once you have this truncated convolutional neural network, you can then use it to project new kinds of new images into different points in some high-dimensional space. So here I'm using the dimension-reduced function in Mathematica in the Wolfram language to project this into 3D. So you can see that different known classes occur in different parts of this space. Now, suppose a new class which it has never seen. This is a class that we don't know about. So I'm just simulating a reverse chirp-shaped signal. So if this occurs, you can actually find that these signals are all clustered in this region of parameter space. So using this unsupervised clustering technique, you can find new kinds of objects which there are no labels for by just looking at these projections. And then you can use that feature extractor and the feature space plot function to just group together all kinds of similar looking signals in the LIGO data stream. So to do that, it's actually very easy. So you have this pre-trained net. Now you again cut off its last layer. So you just take up to the fourth last layer. So now you have this net which takes an image as input and projects it into 2048 numbers. And then you can, so these are all the unknown classes in the test set. So these are the positions of the unknown classes in the test set. These are none of the above. And now you use feature space plot with this feature extractor, and you get, so this net was not actually trained. If you actually train it, you find groups of clusters in different parts of the 2D space. So this is an automatic way to find objects that you don't know about. So this actually shows you how different. These are all similar looking types of signals. All right, so the next thing that we are doing is called denoising, where you have input data. So you have input data which is very noisy, and you want to just remove the noise and see the clean signal inside it. So this is what we actually are doing right now. So we use a recurrent neural network, which is designed for taking sequences of inputs and producing sequences of inputs as a sequence of outputs. So it's commonly used for translation, voice recognition, handwriting recognition, etc. So you can do anything from one-to-one, many-to-many, all kinds of combinations are possible. So this is really powerful. What we use is something called a long short-term memory unit, which is actually available in the Wolfram language since version 11.1. So here we used a many-to-many model, and we have an encoder which compresses an input time series into just a bunch of numbers called a thought vector. And then we have a decoder that tries to reproduce a clean signal from this set of numbers. So it's called a denoising autoencoder because you have noisy signals as the input and the clean signals as the output. So it's trying to just reproduce what is there in the input without the noise. So it's an encoder, autoencoder. And these are our results. So this is the current state-of-the-art method where they use something called dictionary learning. And you can see that at this high signal-to-noise ratio, their inputs are not exactly matching. Whereas our method is actually matching perfectly, and when there is a signal. And when there is no signal, you just get a flat output. So you can actually see in real time what signals are there in your highly noisy data streams. And we only trained this on Gaussian noise, and then we applied it to real noise. And magically, it somehow worked for real LIGO noise as well, with zero amount of training. You can see that it's matching perfectly almost until the end. So if you actually did use real noise for training, we expect the results would be much better. And when there is no signal, it's a flat line. And when you input these eccentric elliptical orbits, you actually still get pretty good accuracy, even though the networks have never seen this. So it's a really powerful model. So now what we want to do is to apply all these real-time analysis techniques so that we can the moment that you find an event like a binary neutron star merger with gravitational waves, you can then look at the object with telescopes such as the Dark Energy Survey, the Large Synoptic Space Telescope that's coming up, and also with astroparticle detectors like the IceCube, which is a neutrino detector. And once you combine all this immediately, you can actually get new scientific insights, whereas right now, it took almost 10 to 12 hours to see this event after we detected the gravitational wave. So now our group is actually applying deep learning to all parts of this scenario, where we are already applying it to gravitational wave detection. Now we are also applying it to telescopes. We're using 2D convolution neural networks to find transient objects in telescope data. So we have a huge group at NCSA which is working on this right now with over 40 people. So that is it. Is there any questions?